Okay, for example 1, we're asked to classify each of the following functions as even, odd, or neither. So we're going to use this idea later to go ahead and sketch out some of the properties of the function. So symmetry, okay, knowing whether a function is even, odd, or neither will help us in sketching a graph. So even functions, very quickly, even functions are symmetric along the y-axis, up and down. So an even function typically will look maybe something like this. Okay? And so if you notice, we have symmetry along this line. If we fold it over, we'd have the same thing. Now what gives us that symmetry is the following. If you take a point, let's say a point right here, it's symmetric, its partner is over here. Now what I want you to notice is that if this is x, then this distance right here, so this distance is x, then this distance right here must be negative x. So what it tells us, if this is a function f, it tells us that f at x gives us a height out, whatever the height is, but that height is the same as the height when you plug in negative x. These guys both have the same height. Okay? That's why this is the property of an even function. So this thing holds for all x in the domain of the function. Okay? So that is the even. This is the even property. So if you look at your function and you play around with it algebraically and this is equal to this, then it has this even property and it's symmetrical on this line. Now there are odd functions out there, and those have symmetry. It's called point symmetry, symmetry on the origin. So what do those guys look like? Well, a very classic example is the cube function. Okay, and so the property holds like this. If x generates a guy out here, I don't know, a height f of x, then its negative x should generate a guy that's got the same height but in the opposite direction. So negative f of x. So, whoops, I want to, so this is f. This is f of negative x, but notice that its height is the opposite of f of x. So this leads us to the following, that the function evaluated at negative x is this height, which is equivalent to the opposite of this height right here. That's it. And so this property is the odd property. This holds for all x's which are in the domain of the function. So these are our two properties. Now if neither of these properties hold, then we say that the function is neither even nor odd. So let's take a look at our three examples for A. Now you've got to prove, you've got to show that these functions are even or odd. You can't just say, oh, it's even or oh, it's odd because I looked at my graph. We actually have to verify it. So here's how you verify it. Don't tell me all the powers are even. Okay, that's not verification. And I won't accept it on an exam. So we need to verify this. So let's say we believe that it's even. To verify that it's even, we must show that f at negative x is the same as f at x. Or we don't have to use x. We could say that f at negative a is the same as f at a for all a in the domain of f. Okay, so let's check this out. Well, f at a, this guy right here, is equal to a to the fourth plus 3a squared plus 12. f at negative a, which is this guy right here, is equal to negative a to the fourth plus 3 times negative a squared plus 12. This guy reduces to a to the fourth plus 3a squared plus 12. This is equal to this, which implies that f of a is equal to f at negative a. And so now we've shown that this function is even. Now, is it possible for a function to be both even and odd? Well, that's a good question. Okay. Now, it's possible for a graph to be even and odd, or for a relation to be even and odd. Clearly, we can look at a circle. A circle centered at the origin is both even and odd. Now, you should think about whether it's possible to have a function other than a circle, okay, but to have an actual function, not just a relation, which is what a circle is, but if we can have that to be possibly be both even and odd at the same exact time. Okay, so let's look at B. So B is equal to x over 1 plus x squared, like that. So we might test. We might say, well, we think it might be even. So let's see if g of a is equal to g of negative a. That's our question. So g of a would be equal to a over 1 plus a squared. And g of negative a would be equal to negative a over 1 plus negative a squared, which is negative a over 1 plus a squared. These guys are not equal to one another. So now let's try to see the odd, see if if it's an odd function. So what we'd want to check is g of negative a, is that equal to negative g of a? Well, we already have these guys calculated. We know g of negative a is this guy right here. So that's negative a over 1 plus a squared, like that. And we know that negative g of a is the opposite of this, which is also negative a over 1 plus a squared. So this passes as an odd function. And this right here, that's our proof. Now let's take a look at C. So for C, we have h of x, and that's equal to x over 1 plus x. So let's check this out. Let's compute h of negative x. That'll give us negative x over 1 minus x, like that. Negative h of x will give us negative x over 1 plus x. Now notice that none of these three are the same. So since none of them are the same, this function is neither.